Hi class, let's take a look at the last of our fronts that we're going to be examining. That's occluded fronts. And so for this example, what we're going to do, we're going to look at a low pressure and a cold front and a warm front on 3 consecutive days as it crosses the United States. And so remember that air masses move at different speeds, that the fronts are the leading edges of air masses, and we know that cold fronts typically move faster than warm fronts. And so on day 1, we've got a low pressure, cold front, warm front. Behind the cold front is continental polar air. Behind the warm front is maritime tropical air. Ahead of the warm front is a retreating continental polar air mass. All right, so I've drawn a cross section from A to B on day 1, and so let's take a look at what that cross section is going to look like. And so we would have the continental polar air right there. We would have the maritime tropical air here, and the warm front would be represented here, and again that will be a wedge of continental polar air over which the maritime tropical air is rising. Okay, and in the center here, here's where our low pressure is. So the important thing on day 1 here is that notice here where the maritime tropical air is, we've got this corridor open. And the importance of that is that warm, moist air, the maritime tropical air, will be drawn into the low pressure. And why is that important? Well, maritime tropical air is warm and moist, and the moisture is the important part in particular here. That moisture is the fuel for any storm system, including just an ordinary low pressure. So we had to expend or provide 600 calories of energy per gram of water to evaporate the water, go from its liquid phase to its vapor phase. Now when this water vapor is drawn into the center of low pressure, it's lifted and it condenses from vapor back into liquid to form clouds and precipitation. And in doing so, going from vapor back to liquid is going to release 600 calories of energy per gram, and that's the fuel for any storm system. Okay, now we move ahead to day 2 and notice that our cold front has moved faster than our warm front and is beginning to catch up. Okay, so we've got again the leading edge of a continental polar air mass represented by the cold front, the leading edge of a maritime tropical air mass is the warm front. This continental polar air is kind of the wedge of a retreating continental polar air mass. So we've drawn in again the cross section here from A to B, and so what this will look like is, again, we'll have our continental polar air and our maritime tropical air, and again our continental polar air here. So notice what has happened here. The corridor is still open, so we can write that in there. So the corridor is open for maritime tropical air to be drawn into the low pressure. But notice that that corridor is getting smaller. Okay, so there's still a bit of an opening here. Okay, but that corridor is getting smaller. So at this point, this is typically when the low pressure is reaching its maximum intensity, that the fuel for the storm system is still being drawn into the low pressure. Water vapor is being condensed into liquid water, releasing 600 calories of energy per gram, and the low pressure is still growing, but it's reaching its maximum intensity at this point. Okay. On day 3, notice now that the cold front has caught up to the warm front, that the continental polar air mass, the leading edge of that continental polar air, is still here. Maritime tropical air is here, but you'll notice that now we've reached what's called occlusion. The cold front has caught up to the warm front, and as a result, the fuel, the moisture, warm moist air from the maritime tropical air no longer can get into the center of that low pressure. So what this would look like on our map would be, or on our cross-section, sorry, be something like this. So here's your continental polar air. The warm front's been lifted up, and continental polar air here. Okay, so at the surface, the corridor is now closed. Okay, and as a result, no maritime tropical air is being drawn into the low pressure. And so as a result, this low pressure now is going to start to dissipate. Okay, so the low pressure without the fuel to keep it going will start to decay, start to dissipate, however you would like to think of it, and the low pressure is going to weaken. Okay, so that concludes Chapter 10 on air masses and fronts, and next we'll take a look at thunderstorms.